Hello, welcome to another module in this massive open online course. So, we are looking at practical applications of optimization. In particular, we have looked at beamforming, that is how to focus the beamforming, the beam in the direction of a particular user, correct, which is termed as beamforming. Let us now extend this paradigm to look at beamforming with interference. That is what happens when you have a desired user and also an interfering user. Okay, so we want to look at beamforming with interference, something that we have not looked at so far. We have simply considered a single user interference. Okay. So, what happens when you have a desired user as well as an interfering user? So, you have again as usual you have this multiple antenna array, and now you have a user to which you want to transmit, let us call this or user who is the desired user whose signal you want to receive, and you have another user who is an interfering user whose signal you want to reject. So, this is the receiver. You want to form a beam in the direction of the desired user. At the same time, you want to reject, correct, you want to reject the signal from an undesired user. So, this is, let us say, your interfering user. Okay. This is your interfering, or this is your desired user actually. Okay. So, this is your desired user, and this is your undesired, or you can call this as your interfering user. So, you want to receive the signal or focus your energy in the direction of the desired user, while at the same time rejecting, correct, rejecting the signal from the undesired or the interfering user. And this can occur in several scenarios. For instance, you have several users, you want to focus on one particular user, or you have, for instance, a cognitive radio scenario, in which case you have the secondary user and then you have the interference from the primary user. Alright, so you want to reject the interference from the primary user, while at the same time focusing your energy while transmission or receiving the signal from your secondary user. Okay. So, for instance, you can think of this as an interesting application in the evolving paradigm of cognitive radio, in which you have Tx1 equals your secondary user. So, you want to receive the signal from the secondary user, but there might be an ongoing transmission of the primary user Tx2, that is the undesired user, that is at the secondary receiver is the primary user. So, you want to reject at the secondary. So, this Rx can be the secondary receiver. Okay. Secondary user receiver, or you can also think of this as a secondary base station. At the secondary base station, you want to get the signal, correct, you want to beamform such that you receive the signal from the secondary user while rejecting the interference from the primary user. Okay, because the primary user is the licensed user, and the primary user has priority for the transmission. So, when there is an ongoing primary transmission, how do you make sure that this does not impact the signal reception, the signal quality at the secondary user? Okay. So, this has many applications, there are several applications in fact, beamforming in the presence of interfering users. Okay. The received signal, now remember the signal model is as follows. Previously we had, without interference, we had y bar equals h bar x plus, you can think of this as n bar. So, desired signal plus noise. Now, you will also have the interference. So, previously we simply had h bar x plus n bar. Now, you have this additional component which is basically your interference from the interfering user. So, this is as usual, this is your noise, alright, ideal white Gaussian noise. This is your desired signal. And so, therefore, G bar xi plus n is the noise plus interference. You can also call this as n tilde. This is equal to, you can call this as n tilde. This is your noise plus you can also think of this as multi-user interference, because this interference is arising because of other users. So, this is noise, unlike for instance, let us say intersymbol interference, this is your multi-user interference arising from the other users. Okay. So, you have noise plus interference, and now we want to compute the noise plus interference covariance, the covariance of the noise plus interference. Now, this is simply your expected value of n tilde transpose. Remember, this is the definition of the covariance matrix, assuming that expected n tilde equals 0. This is a typical assumption, that is the noise mean. We have already seen that the noise is 0 mean, also assume that the interference is 0 mean. So, the noise plus interference will have 0 mean, okay. And then the covariance matrix will be expected value of n tilde plus n tilde transpose, which is expected value of, well, that will be G bar xi plus n tilde, or G bar xi plus n bar times G bar xi plus n bar transpose, which is the expected value of, well, you have G bar transpose xi square plus, let me write this as follows, G bar xi n bar transpose plus xi into n bar into G bar transpose plus n bar transpose. Now, this can be simplified as follows, taking the expected value inside, this is G bar trans. By the way, G bar, now remember, H bar is the channel vector of the desired user, okay. As per our, this is all according to previous notation, channel vector of desired user. And similarly, G bar, which is the L dimensional vector corresponding to L antennas, this is the channel vector of the interfering user. This is the channel vector of the interfering user, okay. So, that is your G bar. So, you have G bar transpose times expected value of xi square plus G bar expected value of the symbol of the interfering user, that is xi, times n bar transpose. Remember, xi, this is basically your signal, or you can think of this as symbol of the interfering user, plus you have expected value of xi into n bar into G bar transpose plus expected value of, this is the noise covariance, that is what we have previously seen, n bar transpose. Now, what we will do is we will assume the symbol power to be p, which means expected value of xi square or pi or sigma I square. Let me just write this as sigma I square. So, we are assuming that the signal power or the interference power is sigma I square, expected value of xi square is sigma I square. Now, we have this quantity which is interesting, the cross correlation, this is expected value of xi n bar transpose, expected value of xi into n bar, that is, it looks at the correlation between the signal and the noise. Now, typically the signal and the noise are uncorrelated, because the noise arises from the system and the signal from the information that intends is information that corresponds to the particular either desired user or interfering user. So, the signal and noise are typically uncorrelated, in fact they are independent. So, if they are both 0 mean, then expected value of xi into n bar, expected value of xi into n bar transpose, both are 0. Okay. So, this is the other assumption, which is of course very intuitive, but needless to say, but nevertheless it can be better, I think deserves, it's worth clarifying this, that is expected value of xi n bar equals, or these are not equal, in fact this is one is a row vector, the other is a column vector. So, expected value of xi n bar transpose is 0, expected value of xi n bar equals 0. So, both these quantities are 0 and the reason is the same, because signal and noise are independent. In fact, what we need is simply uncorrelated, and that signal and noise are uncorrelated. Okay. Typically that is what you have, and therefore, what you have is you will have sigma I square, and this we know noise covariance, this is simply sigma square times identity metric, because the noise samples are, we have assumed the noise samples of the different antennas to be IID, independent identically distributed. So, if you look at the covariance, that is simply sigma square times identity. Okay. So, finally, what you will get is, if you call this noise plus interference covariance matrix as R, what you will get is sigma I square times G bar transpose plus sigma square times identity. Okay. So, this is your noise plus interference covariance matrix. This is your noise plus interference covariance matrix corresponding to this scenario of multi-user beamforming with interference. Now, again we want to find the beamforming vector W bar. How are we going to find the beamforming vector W bar? So, our intention is to now perform beamforming, and for that we need to have the beamforming vector. How are we going to find the beamforming vector? Well, let us say W bar is the beamforming vector. Okay. W bar transpose Y bar, you are doing beamforming. Remember, this is also known as electronic steering, that is, you are simply linearly combining the samples of the received signal. It is a weighted combination, a weighted linear combination of the samples of the received signal, that is W bar transpose Y bar. W bar is the beamforming vector. W bar transpose, substituting Y bar, this is Y bar times H x plus now n tilde, where n tilde is the noise plus interference, this is, well, again this is W bar transpose H into x plus W bar transpose n tilde, this is the signal. This is the signal gain, in fact, W bar transpose H bar, and this is the noise plus interference. Now, not simply the noise. Okay, so this is the noise plus interference. Now, what we want to do is we want to minimize the effect of this noise plus interference at the output. So, we have to calculate its power. So, while setting the gain in the direction of the signal. Now, this is something that you have to pay attention to, the reason being the follows. If you simply minimize the noise plus interference without, consider this optimization problem where you simply minimize the noise plus interference or the noise without paying attention to the signal, alright. So, all you want to do is minimize W bar transpose N tilde, then the optimal value of W tilde or W bar beamforming vector will simply be 0, because if you use beamforming vector to be set it to be 0, then the output noise is 0, but the problem with that is the output signal is also 0, alright, and therefore, and you cannot have that, alright. So, therefore, you have to minimize the noise or noise plus interference while restricting it, constraining it in such a way that the signal is not affected, that the signal gain is still unity, alright. So, that is the important aspect to pay attention here. So, we want to minimize the noise plus interference. What is the noise plus interference power? That is W bar transpose N tilde. We will calculate this in a compact fashion, expected W. Now, this is a scalar quantity, so I can do all kinds of manipulations, that is W bar transpose N tilde times itself. Scalar quantity is scalar quantity transpose, so I am going to simply write it as W bar transpose N tilde transpose, which is nothing but W bar transpose N tilde square. Now, this is expected value of W bar transpose N tilde transpose into W bar. And now you have something interesting. If you take the expected value inside, you have W bar transpose expected value of N tilde transpose W bar, which is W bar transpose expected value of N tilde, this is nothing but the noise plus interference covariance. So, this is W bar transpose, this is R. Okay, expected value of N tilde transpose, this is the noise plus interference. So, this is the net noise plus interference power at the output of the beamformer. So, this is your noise plus interference power at the output, noise plus interference power at the output of the beamformer. And now, what is our optimization? Now, again we want to have, remember, signal gain W bar transpose H bar, this has to be 1. So, signal gain has to be unity. So, what is our modified optimization problem for this beamforming with interference? So, the optimization problem for beamforming with interference. So, the optimization problem for beamforming with interference is minimize, that is what we have seen, minimize the noise plus interference power, which is what we have calculated, W bar transpose R W bar. Previously, this was simply W bar transpose W bar, if you remember. Previously, this was simply W bar transpose W bar equals norm W bar square, okay, when the noise, when you simply add noise. Now, you have the noise plus interference, therefore, is W bar transpose R W bar, where R is the noise plus interference covariance, that is the only difference. Subject to their constraint, what is your constraint? Constraint is, well, W bar transpose H bar equals 1. Gain in the direction of the signal equals unity. All you have to do is now form the Lagrangian f, which is W bar transpose R W bar. Now again remember the covariance matrix is positive semi definite, this is a positive semi definite matrix, implies, now that is always important to check, implies W bar transpose W bar is convex, okay. So that is an important thing. So this is a convex optimization problem because the objective function is convex, that is something that you have to verify at each and every stage, that you are solving indeed solving the right kind of problem, okay. So this is W bar transpose R W bar, and then usually have you, as usual you have the Lagrange multiplier 1 minus W bar transpose H bar, 1 minus W bar transpose H bar, and now differentiating this, W bar transpose R W bar, because R is symmetric matrix, this is simply twice R W bar minus lambda, derivative 1 is 0, W bar transpose H bar derivative is